Hello everybody, welcome to 4-4, adding and subtracting rational expressions. You know you're getting into complex math when the adding and subtracting is harder than the multiplying and dividing. Alright, so first let's just break down kind of what we're going to be doing for this lesson in the most basic way possible. So let's just talk about if we're adding fractions. Let's say I have the problem 1/3 plus 1/4. Now there's a couple ways you can look at this. First thing we could do is just list all of the multiples of each number. This is like how you were taught a long time ago, right? Just list all the multiples of 3, list all the multiples of 4, and so forth. And we'll get to the point where we can find the multiple that they share, that is the lowest number, and we're going to turn both of these into a fraction that has that as the denominator. So the way you would do that is, okay, I would put 12s on the base, and then I would say, okay, what times 3 gives me 12? Well, it's 4, so this will become 4/12. And then what times 4 becomes 12? Well, it's 3, because we have to multiply the numerator and denominator by the same number. So the other way you could look at this, right, and we're going to get 7/12. I didn't want to hold you in suspense for too long. There we go. All right, the other way we could look at this is if we know that 12 is our number, well, we can take our original 1/3, and we can take our original 1/4, and we can actually multiply both sides by 12 and then reduce in the end. So what I'm going to do, just to kind of show you how this works, is 12 is basically the combination of these two numbers. It's 3 times 4. So what I'm going to do is I'm going to multiply the top and bottom on both sides by 3 times 4, just to kind of show you how this works, essentially. Because this is ultimately what we're going to be doing, right? When we do more difficult expressions. All right, so when we do something like this, we're going to multiply the top, right? And we have the top and the bottom, but we can reduce things that we don't have, right? So in other words, if we look at the numerator here, we have a 3 times 4 times 1, and down here we have a 3 times 4 times 3. Well, the idea behind this is that we can like use this to turn this into a fraction that looks like that. So if we need to turn this into, and we need to turn this into a 12, right? The 3's could cancel, the 4's would turn this into a 12, and then the 4 is what's left over. I realize this looks like nonsense because you would never do this in a problem, but the idea is you can see that these multiples are what's being used to create the 12, right? That's why we're getting a common denominator. So I guess in this one, right, we could eliminate the 4's so that we could create a 12 down here, right? So anything that's same on the top and bottom, we can kind of get rid of. So we didn't need the 3's on this side, and we didn't need the 4's on this side, okay? It's a very long explanation, but it kind of shows you exactly what we're going to be doing going forward when we actually get into rational expressions. All right, adding rational expressions with like denominators. Well, just like with fractions, right? If we have two fractions with the same denominator, we can just add across the top. So let's look at this first one. We have x over x plus 4 plus 5 over x plus 4. Well, we have x plus 4 in both denominators, so we can simply say this is x plus 5 over x plus 4. And you'll recognize that x plus 5 is simply x plus 5. There's no like terms we can combine or anything like that. So this is literally our answer. There's nothing more we can do to this. All right, well, let's do another one where maybe we can do something more to it. So let's go ahead and just add across the top, just like before, right? Because we have an x squared plus 3x on both denominators. So we can just add across. Well, in this case, we have a 2x and a 3x, so we can turn that into a 5x. And then we have a 1 and a negative 8, which will become a negative 7. And then along the bottom, we have x squared plus 3x. And the x squared plus 3x, we could pull an x out of both, but ultimately, there's not anything we can pull out of the top, so we're not going to have any common factors. So this is kind of the it. This is kind of it, right? So the goal is to create problems that look like this. If we can make all of our expressions have like denominators, then we can simply add, and we're done. And it's that simple. All right. So now let's get into something a little bit more complicated, finding the LCM of polynomials. Now this is very important because, like we did when we had fractions, we have to find the least common multiple so that we can figure out what we have to multiply by in order to create fractions that have the same denominators, right? So if we look at this, The question is asking, what is the LCM of x plus 2 squared and x squared plus 5x plus 6? All right, so the first thing we're going to have to do is like factor each of the polynomials so that we know what the individual pieces are. And now you can kind of see why over here I showed you all of this, what seems like nonsense, right? Like 3 times 4 times 1. Like, why are you listing all these multiples? Well, that's because that's what we're going to do with these polynomials. We're going to break it down into its smallest factor pieces. That way we know which pieces are shared, what they have in common, and all that. So let's factor each. So x plus 2 squared is, that one's kind of easy, right? That one's literally just x plus 2 times x plus 2. Because it's just that multiplied by itself, right? That's what squared means. All right, and for the other one, it looks like we have a trinomial. So let's see if we can find something that multiplies to get 6 and adds together to equal 5. We have a 6 and a 5. So I see a 3 and a 2. Positive 3, positive 2. So let's look at that. So we have x plus 3 and x plus 2. All right, now when you're finding the least common multiple of polynomials, that's the first step, right? We need to see what each of them are. So we have this part over here, and we have this part over here. All right, now take every unique factor. So unique factor means something that looks different. So you'll notice that here we have x plus 2 and x plus 2. Those are not unique factors. Well, one of them, I guess, is unique, but those two are the same. So there's only one unique factor there. And then over here we have x plus 3 and x plus 2. So take every unique factor. So what we're going to do is we're just going to put x plus 2 as a unique factor, and then we're going to take, well, x plus 3 as a unique factor. These are all of the unique factors that exist between both of these polynomials. All right, now the last thing we're going to do to finish our LCM is we're going to take the most of each factor. So in other words, if we look at this first set of factors here, we have x plus 2, but we have it twice, right? And over here, we have x plus 3. That's the most, right? Because we don't have an x plus 3 over here. So we're going to take 1x plus 3, and we're going to take 2x plus 2s, because even though this has an x plus 2, this isn't the one with the most, right? The one with the most x plus 2s is over here. So this is going to be x plus 2 and x plus 3, but when we take our LCM is actually going to be x plus 2 times x plus 2 times x plus 3. And this is because your LCM has to include the most of each unique factor, and it has to include every unique factor. So ultimately, to finish up the problem, it's going to look like this. We can just combine these x plus 2s. So you could say x plus 2 squared times x plus 3. Or you could honestly just leave it like this. Like, that's probably going to be more useful for our problems. But this is how you find the LCM. And this will be very important because, just like when we did problems before, right? You need to find the LCM in order to be able to add the top, because we need the denominators to be the same. So we need to be able to find the LCM. That way we can fix our denominators so that we can do that. All right. So now we're going to get into the big stuff here. Adding rational expressions with unlike denominators. This is going to be us factoring and then finding the GCF and then going back and forth between simplifying and factoring until it kind of gets into its final form. So let's just do it. All right. So factor the denominators. That's the first step. So here we have x plus 3 over x squared minus 1 plus 2 over x squared minus 3x plus 2. All right, so let's factor the denominators. So we're going to have x plus 3 on top over, well, x squared minus 1. Hopefully you recognize that as being a difference of squares. And if you don't, go look up difference of squares. This is going to be x plus 1 times the quantity x minus 1. Hopefully you recognize that pattern. And then plus, let's factor the other side. 2 doesn't factor at all. It's literally just an integer. And then we have x squared minus 3x plus 2. So what numbers multiply to get positive 2 that add to get negative 3? I'm thinking negative 1 and negative 2 would work for that. So let's do it. X minus 1, x minus 2. Okay. So find the greatest common factor. Well, that's kind of what we were doing before, right? The least common multiple was over here. Basically what we're going to be doing is we need to find, if we think of it this way, right? What is the piece, I guess this should be, not GCF, we're finding the not the GCF. We are finding the least common multiple. Okay, so when we find the least common multiple, we're going to just do what we did before, right? We're going to find all unique factors, and then we're going to find the one that has the most of each. So here I see an x plus 1 and an x minus 1, but only one of each of those. So x plus 1, x minus 1, and then over here I have x minus 1. So that's already, we already have a one of those, right? And there's not two of those, so we can just kind of keep that there. And then we have x minus 2, which is also unique. So our LCM are all three of these multiples. Okay, that's pretty straightforward. And you'll notice we don't have to like take multiples of one of them because there's only one of each of them on each side, right? Okay. So multiply both addends with GCF. This should not be GCF. This should be LCM. All right. So essentially what we're doing is let's think about what we did when we did fractions, right? If we go back here, if we had 1/3 plus 3, or 1/3 plus 1/4, we multiplied the 1/3 by 4/4, right? We took all of the pieces of the denominator that we don't have, right? Which in this case was a 4, right? Because we need to, in order to get from 3 to 12, we have to multiply by 4. So we're missing a 4, right? So in order to get this to become a 4, we have to multiply the top and bottom by a 4. Well, it's going to be the same thing here, right? So if I look up here, if I look at this first denominator, or this first expression here, rational expression, I have an x plus 3, and I have an x plus 1, x minus 1. Well, if I look at my LCM, I need an x plus 1, an x minus 1, and an x minus 2. So what I'm going to do is just like before, I'm going to multiply the top and bottom by the piece that I'm missing. So what I'm going to do is for step 3 here, I'm going to take x minus 2 over x minus 2, and I'm going to multiply that by x plus 3 over x plus 1, x minus 1. And all of these pieces are just being multiplied together. All right, so now we're going to do the same thing to the other side, right? We have a 2, and we have an x plus 1 and an x minus 2. Well, over here, or x minus 1, x minus 2. So over here we have an x minus 1 and an x minus 2. We need this x plus 1. So what I'm going to do is I'm going to take this and I'm just going to go, okay, 2 times the quantity x plus 1, right, over x minus 2, x plus 1, and x minus 1. And wouldn't you know it, the reason we did that, of course, is that we get the denominators to be exactly the same. Here we have x plus 2, or x minus 2, x plus 3, over the denominator, right? And over here we have 2 times the quantity x plus 1 over the denominator. All right, multiply the numerators and combine like terms. Okay, so now we're basically, like I said, we're going to go back and forth between the step of simplifying and then factoring and then simplifying and then factoring, right? Until we get it in its ultimately its simplest form. So what we're going to have to do up here is we're going to keep the denominators the same, right? Because we know what the denominator is. That's not really a big deal. What we're going to do is we're actually going to take these numerators up here and we're going to FOIL them. We're going to FOIL this and then just distribute this, right? And then we're going to combine all the like terms up top because we can do that now because we have the same denominators. And then we're going to see where that gets us. So let's go and do this. So we have x minus 2 times x plus 3, which will give us x squared minus 2x. Here, I'll just do it. So minus 2x plus 3x. Hopefully you get faster at this pattern if you're not already, right? And you'll notice that the negative 2x and the plus 3x will combine. So we'll have x squared plus x minus 6. And then on the other one, we have 2 times x plus 1, which is just 2x plus 2, right? And then I'm just going to bring this down here. You'll notice that we're just adding these across, right? We have this here plus this here, and we have the same denominator, so now we can just add across like we did in the last problem. So we have x squared plus x minus 6 plus 2x plus 2. And then, of course, all of this is still over the same denominator. We're just solving the numerator for now. So now we're just going to combine like terms. So I see here I have an x and a 2x. And then I see here that I have a negative 6 and a positive 2. So let's combine all those. So I have x squared plus 3x minus 4. Hooray. Okay. So this is just our numerator. Of course, we have this. So x squared plus 3x minus 4. And this is going to be over our denominator. And we're just going to keep this in its factored form because this is going to make it easy for us here in a second. X plus 1, x minus 1. Okay. Now, factor the numerator and simplify. So again, we added them together, we simplified. Now we're going to factor again. This is what we're going to do until we get this in its most simplified form. Because now you'll notice that we haven't done nothing, right? We went from two separate rational expressions to now just one rational expression. So we are making progress, right? The last part of this is going to simply be factoring the top, seeing if there's anything we can cancel, and then we'll be done. So factoring the numerator and simplify. What do we have that multiplies to make negative 4 that adds to make positive 3? Well, the answer to that is positive 4 and negative 1, right? So if we take the top and we factor it, so we're going to factor x squared plus 3x minus 4, and this is going to become x plus 4, right? Because we need the 3 to be positive, and then x minus 1. And then the whole denominator is x minus 2, x plus 1, and x minus 1. All right, awesome. So what do we do now? Well, we have an expression here. When we did dividing or multiplying, we could eliminate, right? So we have x minus 1 on the top and x minus 1 on the bottom, right? And what this will tell us is that our final form here is just x plus 4 over. If you want to FOIL this, you can. It would give you, the answer would just look slightly different. Just make sure that you look for the answer that makes sense, right? Obviously, on an exit ticket, if this doesn't look exactly like this, you may have to FOIL it and get the right answer. All right, now I just want to analyze a few things here because there are a few things that are true, right? A couple things that are true are there are going to be certain places that our domain cannot exist, right? So our domain is x such that x cannot equal what? Well, x in this case, we have to look back at the original expression, right? When we finally broke all this down, our LCM was this, right? What's along the bottom? So x cannot be positive 2, negative 1, or positive 1. It can't be all of them. And I'm going to show you what the difference is between these ones that are crossed out here in a second. So we have x cannot equal 2, it cannot equal negative 1, and it cannot equal positive 1. These are all of the exclusions. Now, you're probably like, Mr. Moneypenny, there's got to be something cool about the idea that both of these minus ones were eliminated. And if you know anything about math, there's always something cool. So let me show you this real quick. So let's go back. We have, let's go to here, x plus 4, x minus 1. X plus 4, x minus 1. We're going to do all of that over, wrong thing, x plus 4, x minus 1, x minus 2, x plus 1, x minus 1. X plus 2, that's a 3. X plus 2, x plus 1, x minus 1. All right, now let's zoom in a little bit here so we can see. And you'll notice that as far as asymptotes go, okay, well, x plus 2, so we said it can't reach minus 2, right? Well, let's zoom in a little more. Here's negative 2. And you'll notice that if you look at this graph, it's going to do everything in its power to never hit negative 2, right? So that kind of shows that that one's right. All right, well, what about, okay, plus 1. It can't be negative 1. Okay, well, let's see if that looks right. Ooh, okay, here's negative 1, right? Does it ever, 0. Oh, that's -1. -1 would be right here. Sorry, it's a little bit smaller. So -1's right here. Does it ever hit -1? No, it does not. It's going to do the same thing. It's going to do everything in its power to never touch it. In fact, it can't touch it, right? And now you're like, ha, gotcha, Mr. Moneypenny. Look at this. X minus 1. That means it can't be +1. If I look at +1, clearly it touches +1, right? Well, let me show you something cool. If you go to 1 here, what do you see as your y value? It says it's undefined. So when you have the same factor in the numerator and the denominator, it doesn't create a vertical asymptote. It creates a hole. So if you were going to graph this more properly, you would actually put a hole right here, and you wouldn't make this one continuous line. So I just thought that was interesting. I thought I would show you that. So anytime, if we look at our equation over here, right, the x plus 2 and the x plus 1, both of those, because they're not shared in the numerator, will create vertical asymptotes, which we just saw. Now, because the x minus 1 is shared, then the 0 of that, which would be 1, it doesn't exist on the graph either, right? We proved that it can't, because we can't have a 0 in the denominator, right? But in this case, it's not an asymptote. It's actually a hole, which is just really neat. All right, so let's go back to the math here, now that we got to look through Desmos a bit. All right, so subtracting rational expressions. This is exactly the same thing, except for in this case, we're going to subtract when we combine like terms instead of add when we combine like terms. And that's borderline the extent of it. So this will more or less give us some practice on kind of the last thing we did. So first thing is we have to figure out what the factors of the denominators are. So we have x squared minus 6x minus 16, and we have x squared plus 6x plus 8. So let's look at this one. What numbers multiply together to get -16 that add together to get -6? I'm going to go with -8 and +2. So x plus 1 over x minus 8, x plus 2. Okay, and now minus, we have an x plus 1 up here. We have x plus 1s everywhere. And then on the bottom, we have what multiplies to get 8 that adds to get 6. That's going to be 4 and 2. So we're going to do x plus 4 times x plus 2. And now we have to find the least common multiple, right? So our common multiples here, it looks like they both have an x plus 2, and then the ones that they're not sharing are going to be the x minus 8 and x plus 4. So the LCM is going to be x minus 8, x plus 2, x plus 4. And neither of them have more than one of these multiples, so that's going to be it. So let's do it. So on this one here on the right, or on the left, we have x minus 8 and x plus 2, which means the one that we're missing is the x plus 4. So we're going to have to multiply the top and bottom by x plus 4. So this is going to be x plus 4 times x plus 1, and that's going to be over x minus 8, x plus 2, and then the new addition, which was the x plus 4. The order of these don't really matter, right? Because they're all being multiplied together. And then minus, well, let's look at this. So we have x plus 1 up here, right? And in this case, we didn't have the x minus 8. So we need to multiply both of these by top and bottom by x minus 8. So this is going to be x minus 8 times x plus 1. All over the same thing, right? X minus 8, x plus 2, x plus 4. Okay, so now we have to FOIL the top. So over here we're just dealing with numerators now. So we're going to have x squared plus 5x plus 4. And then minus, over here, we have x squared. -8 and 1 is going to be minus 7x. And then minus 8. All right. And just like before, we just have to combine like terms now. That's all we have to do. So let's use some color here just for fun. So we have x squared and -x squared. Ooh. And then over here, we have, what, a 7x and a 5x. oh, critical, don't make this mistake, right? This is negative this expression, right? You see this? So what we have to make sure that we do is we have to make sure that we distribute this negative to the expression, right? So this isn't just a negative x. This is actually, this will stay the same, right? X squared plus 5x plus 4. And then over here, we're going to have negative x squared plus 7x plus 8, right? The negative distributes to all three of these pieces. Okay. Yeah, definitely don't make that mistake. Like, I was just about to. All right. Caught it in time. Okay. So, x squared. That's fun. And then let's go with this nice magenta color. And then orange. That sounds cool. Okay. So x squared minus x squared, zip, and then we have 5x plus 7x is 12x. And then we have 4 plus 8, which is 12. Okay. So 12x plus 12 is our entire numerator, right? And then our denominator is the same as it was before. So x minus 8 times x plus 2 times x plus 4. And now we just have to factor to the top one more time. I can pull out a 12, it would appear. So I'm going to have x plus 1 and on the bottom, I'm going to have x minus 8, x plus 2, and x plus 4. And ultimately, there's not any super satisfying way to reduce anymore, right? So this is, we just got to check and get here and see if there's anything, and there's not. So that's it. So the last thing we're going to do is the domain. The domain is x, such that x cannot equal 8, -2, or -4. And everything on this is going to be an asymptote, right? We don't have any shared from top to bottom. So if you wanted to kind of know what the graph's going to look like, it's, if we graph this, you're just going to see asymptotes at 8, -2, and -4. All right, cool. Let's do one more. So we're going to use rational expressions to solve real-world problems. This is where it gets a little fun, right? I mean, we were having fun before, but this is really fun. So, all right. So let's look at our problem. We have George drives his car to the mechanic and then takes a train back home. The average of a 10-mile trip is 15 miles per hour faster on the train. Find an expression for George's total travel time. How long will it take for him to travel if he travels at a rate of 30 miles an hour? Well, first of all, what is a rate? That's probably these questions always boil down to understanding what that means. So a rate is just, usually it's something over time, right? Like how much, what's your pay rate? Well, that's how much I got paid divided by how much time I worked, right? There's tons of different rates. What's your speed? My speed is the miles per hour, right? So the time component almost always exists. Well, in this case, we're most specifically talking about speed, right? So if we have our rate in terms of speed, it's going to be distance divided by time. Perfect. Now, this is what's important, right? Is it saying how long will it take for us to travel at a rate of 30 miles per hour? So if we're looking for how long it's going to take for us to travel, we're looking for time, right? So we want to rearrange this formula so that we're finding time equals something, right? So if we multiply both sides by time, then divide both sides by rate, hopefully you've kind of seen this pattern before where these kind of can just switch spots, right? So this, so time equals distance over our rate. And now, usually a good way to do stuff like this, like anytime you have problems that deal with like comparing two different like sets of numbers like this, a good way of doing this is usually just kind of make a chart. So I'm going to have a car, and I'm going to have a train, and then I'm going to have my numbers, right? So I'm going to have my distance, I'm going to have my rate, and then I'm going to have my time, which is what I'm trying to find, right? So they're not going to give us the time. We're going to have to figure out the time, because if they give us the time, the problem would be over. So maybe we'll get lucky in a different problem and they'll forget that they're trying to ask us a question. But all right, here's my excellently drawn chart here. All right, so now let's look at what we have. Well, it says the average of the 10-mile trip is 15 miles per hour faster than the train. If he's driving the car to the mechanic and then taking the train back home, he's driving from home to the mechanic and then back home, right? So the distance is the same for both. So it's a 10-mile trip regardless. So 10 miles, right, 10 miles for each. Perfect. Now the rate, this is kind of where this next sentence comes in, right? The average of a 10-mile-an-hour trip, the average of a 10-mile trip is 15 miles per hour faster on the train. So let's say the rate of the car is just the number we don't know, right? We don't know the exact rate. We just know that the train is 15 miles an hour faster. So the rate of the train is just x plus 15. All right, well, the time, we can now figure out the time, right? Because we know the time is the distance divided by the rate. Well, if we know the distance is 10 and the rate is x, then we know that the time is 10 divided by our rate, which is x. So far, so good. Same thing for the train, right? For the train, we're going to have 10 divided by x plus 15. And now, how long will it take for him to travel if he travels at a rate of 30 miles an hour? Well, the 30 miles an hour we'll be able to plug in once we simplify this, right? But for now, we have to know, okay, well, we have to use one rate for the time he's on the car, and then one rate for the time he's on the train. So we know that the total time is going to be the combination of these two things, right? So it's going to be 10 over x plus 10 over x plus 15. And now it looks like a problem that we've been doing this whole time, right? So what do we have to do? Well, we have to find the LCM. So let's do it. We have the LCM. And the way we find that is by factoring. There's not really any factoring to do here because x and x minus 15 are both just factors. So the LCM is just x and x minus 15. It's just both of these numbers, right? Or x plus 15. And think about it. When we would do fractions, right? If the fractions are 3 and 4, right? We just have to multiply 3 and 4 to get 12. Right? There's no cooler way of doing it. It's just what it is. So now we're gonna do what we did before. We're gonna multiply by the pieces we're missing. So on this side we have a 10 over x. So the part we're missing is this x plus 15. So we're gonna have to multiply both by the x plus 15. So this will become 10 times the quantity x plus 15 over x times x plus 15. Right? Because this is just our LCM, right? So we have our combined here over the LCM. And then we're going to be adding this to, well, we're on this side, we have our 10, right? And we have our x plus 15, but we don't have the x on the bottom. So we need to multiply this whole thing by x over x. So this will give us 10 times x. And then on the bottom we have, of course, x times x plus 15. And now we have denominators that are exactly the same. So we can just kind of add across the top. Well, first I'm going to break this up, right? So I'm going to have 10x, 10 times 15 is plus 150. And then plus, over here we have 10x, so 10x. Right? And now let's go ahead and simplify that just a little bit more. And we're going to have 20x plus 150. And that's going to be all over our denominator, which was x plus 15. Right? Okay, now what they really want to know is the answer to the question is how long will it take for him to travel if he travels at a rate of 30 miles an hour? Well, we know that the rate of 30 miles an hour is just x, so we can literally just plug in 30 for x here, and we can get the number. So we're just going to do that. So we have 20 times 30 plus 150, and that's going to all be over 30 times the quantity 30 plus 15. All right, so let's simplify the top. We have 600 plus 150 is going to give us 750. And then on the bottom, we have 30 times the quantity 30 plus 15. 30 plus 15 is 45. 45 times 30 is going to be 1350. All right, and then we can just plug this into a calculator. So 750 or 1350 divided by 750, and you're going to get approximately 0.55 hours. All right, so what's the question here? How long will it take him to travel if he travels at a rate of 30 miles an hour? Well, it's going to take him about a half an hour. Make sense? Well, let's see. So let's go ahead and go back to our expression here. Let's always, you can always use Desmos for everything, right? Let's take a look. So if we have the expression we popped out at the end, we have 10 over x plus 10 over x plus 15. Okay. And the question is, when we are at 30 miles an hour, right? How long will it take him to travel 30 miles an hour? Well, let's go back here. Let's go all the way up to 30. And what's our number here? Well, the closer I can get to 30, 0.34. It would help if I was looking in the right spot, right? There we go. Okay, so 30 and 0.5, right? Because our x value is going to be our time, and that's what we were looking for, is how much time. So we look over here on our chart, and yeah, there we go. 30 and then 0.555556. Yeah. All right, so that's a way we can use Desmos to check our work, just like always, right? So we plugged it in. We determined that where t is about half an hour or 0.5 hours, we are traveling at 30 miles an hour. All right, awesome. Well, that's it for this video. Of course, always make sure to check your domains, right? In this case, it's asking us a specific problem, so we don't really need to establish the domain because that's not really what's important. But yeah, so that's how we can apply the situation. So just a quick recap. What we did is first we looked at fractions in general. That helped us establish a set of conditions where as long as we understand that the denominators are the same, we can combine the numerators. Then we did a bunch of simplifying and factoring back and forth so that we could reduce our multiple expressions into a single expression. And then from there, we just kind of factored it out, eliminated everything we can, and established a domain. And then we solved a really cool problem regarding George's 30-mile-an-hour trip. All right, well, that's it for this video. I'll see you in 4-5.